Hi, my name is Christopher Recchia, and this is Free Fallen, an application of terminal velocity to find drag coefficient. So what is terminal velocity? Terminal velocity is the speed at which an object falls when the drag force becomes equal to the downward force due to gravity, causing a net force of zero and in turn zero acceleration. A simple example of this might be when you're driving in a car. If you were to take your hand and place it out of the window, you would feel a force pressing against your hand as you move. This force is the air resistance, or drag, due to Newton's third law. This was first proposed in Sir Isaac Newton's Philosophiae Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy. Of course, this is a small-scale example, and the drag felt by your hand is nowhere near enough to prevent the car from accelerating. However, there is a way to illustrate terminal velocity using a small household object. This is the terminal velocity equation, and it should be noted for this experiment. We're going to begin by solving for the variable c sub d in the denominator of the fraction. Now that we've done this, we can begin to isolate our variables. The many variables that incorporate into this equation are the mass of any object we're using, the acceleration of the object due to gravity, 9.81 meters per second, the density of air in the space we're using, and the cross-sectional area of any object we're using. Now, our experiment is going to be an investigation of drag coefficient. And now that this is oriented this way, we can use the mass and terminal velocity of any object to create a linear function and find the drag coefficient of an object. Now you might be asking, what object would be very easy to reach drag coefficient? Well, it's something very small, and you find it around your house every day. So, what is the drag coefficient of a coffee filter by using terminal velocity? And hopefully, our drag coefficient will be within 20% of the accepted value of 1.02. So let's begin to talk about the experiment and how this is going to work. Our materials are going to include a TI-84 Inspire calculator, shown here, a Recchia motion sensor, shown there, 10 coffee filters, shown at number 3, a meter stick, so we know how high we're dropping our coffee filters, a stool, so we can reach the appropriate height, a scale, accurate to the milligram, and Logger Pro software used on a computer. So in order for this to work, we measured the masses of 2, 4, 6, 8, and 10 coffee filters stacked on top of one another, then created a position versus time graph with the TI Inspire graphing calculator and motion sensors shown in the previous slide, and ran motion sensors and dropped 2 coffee filters stacked at 2 meters. We recorded the graph and the constant slope from the equation shown before, and repeated steps 3 and 4 for 4, 6, 8, and 10 coffee filters. After this, we take the averages and plot all of our independent variables and dependent variable into Logger Pro, and we were able to compare the observed drag coefficient to our accepted value as previously stated. There are a few notes that need to be made for our calculations. For example, the cross-sectional area is needed. The radius of the coffee filter was measured to be 0.0865 meters, which has an area of 0.0079 meters squared, as well as the density of air. This had to be considered. Because it was difficult to find the density of air of the room used, we approximated the temperature at 20 degrees Celsius, which gives us a density of air of 1.2401 kilograms per centimeter cubed. This will give the experiment some error since the temperature of the room was approximated. Now for our data and the beginning of our analysis. So as you can see the graphs used for the 8 coffee filter trial, and you can see some of our terminal velocities here. You can see 2.845, 2.841, 2.842, 2.841, and 2.841 again. These constant slopes ensured that we were doing our experiment properly and allowed us to continue in the experiment, but also gives you a pretty significant understanding of how minor these terminal velocities actually are. So now looking at our data, we see the mass over here in this column with our number of coffee filters stacked and the terminal velocities reached for each. Now we begin to plot this into our graph, inputting both of these variables, and we will get a linear function telling us the drag coefficient. So as you can see, here's our graph for our drag coefficient. The average slope is 0.83, and our max slope is 0.912 with a minimum of 0.8 rounded to the hundredths place. Now that we've looked at our graph, we can begin to calculate the error for the experiment. The error is calculated by taking the absolute value of our theoretical, which means our calculated value, minus the accepted value of 1.02, divided by our accepted value, times 100 to give us percentage. Plugging those values in, we get an error of 18.46%, which is within our hypothesis of being within 20% error. The strengths and weaknesses of the experiment are important to note. For example, our strengths were finding the drag coefficient within 20% of our accepted value, like we hypothesized in the beginning. We also successfully were able to alter the conditions, so differing values were obtained, even though we were using something very small scale, like a coffee filter. But our weakness was that assumed density of air that we discussed earlier in the presentation. This hindered our experiment and made us prone to more error. So, if I was to suggest an improvement for this experiment, it would actually be to conduct another one prior to this to find the density of air in different rooms and the ideal one for this experiment. The temperature was approximated, as we discussed, with 20 degrees Celsius as our ambient temperature of the room, but finding the exact temperature of the room and then being able to find the density of air due to temperature would have made our values much more exact. And here's the bibliography, and thank you for listening to the presentation.